This video is for ELEC 1510 Logic Design. This is Lecture 12, Part 2 on multiplexers, corresponding to textbook section 4.11. This is a very important lecture. Multiplexers are a very important logic design sub-block that we will use for the rest of the class. So it's very important to understand this material. This is one of the most important lectures, probably. A multiplexer, or MUX, as they're often abbreviated, is a system for routing signals. Multiplexers have multiple inputs and usually only one output. There are select signals as inputs as well to the multiplexer, which allow for choosing which input is routed to the output. A good analogy for this is something like a car stereo, where you've got speakers in your car, and on your car stereo you can have multiple inputs that are routed to those speakers. So you could have an aux cable that then gets routed to the speakers. You could have, say, this would be wireless, but Bluetooth that then gets routed to the speakers. You could have, if your car is old enough, like mine, you could have a CD player that gets routed to the outputs. And you could have FM radio as well. Now you're not going to have all of these get routed to the speaker at the same time. You press a button to tell your car stereo which one of these actually gets routed to the speakers. Multiplexers work like this. They have multiple inputs and then select lines that tell the system which one of the inputs actually is going to appear at the outputs. The symbol for a 2x1 multiplexer looks like this. It's sort of a trapezoid shape turned on its side. It has two inputs, and I'm going to call those inputs W and Y. I'm leaving out X because we're going to have don't cares in the truth table, which are represented by X's, so that would be confusing if I also had X as an input. The select line is right here, and that has the symbol S for select, and then the output is Z. Now you can see that W corresponds to 0, Y corresponds to 1, and this refers to the state of the select line. So when the select line is a 0, then the signal corresponding to 0 gets routed to the output. When the select line is a 1, the signal connected to the input 1 is routed to the output. So then the truth table, or I should probably say pseudo-truth table, for a 2x1 multiplexer looks like this. When the select line is 0, the output Z is equal to W, and we don't care what W is and what Y is. They could be anything, but Z is going to be equal to W in that case. If the select line is 1, again, we don't care what W and Y are, but Z is going to be equal to whatever Y is. So then the logical function that actually exists inside the 2x1 multiplexer implemented with gates is Z equals S prime W or SY. So here we see the diagram for an 8x1 multiplexer. If you have an n/1 multiplexer, you need log base 2 of n select lines. So you can see here we have 8 inputs, I0 through I7, and log base 2 of 8 is 3, so we have 3 select lines, S2, S1, and S0. The function representing the output Z is fairly long, but we can approximate it by just listing it like this. Basically, it follows a pattern. Z equals S2 prime, S1 prime, S0 prime, I0. That means that if all the select lines are 0, then I0 is going to appear at the output. If the select lines give you the binary number 1, that's S2 prime, S1 prime, S0, so that's 0, 0, 1, then I1 is going to appear at the output, whatever the state of I1 is. And it'll follow that pattern until finally S2, S1, S0, meaning all the select lines are 1, and whatever state I7 is in will appear at the output. You can get larger multiplexers as well, 16 by 1, 32 by 1, 64 by 1, etc. You just need more select lines as the multiplexers get larger. Okay, so similar to decoders, multiplexers are elements that can be used to implement general types of logic functions when represented as truth tables. There's a pattern that you need to follow in order to figure out how to implement a general logic function using a multiplexer. First, you use the most significant bits in the truth table inputs as select lines. So if you have n inputs in the truth table, you would use n minus 1 of those and the most significant n minus 1 of those as select lines. And then you use combinations of the least significant bit as the multiplexer inputs. So I'm going to do a few examples of this just to show you how it works. Let's say that we have a function with inputs a, b, and c and output z that looks like this, specified by this truth table. So what we're going to do is block off sections of this truth table where the most significant bits a and b are set to the same value. So first, a and b are 0 and 0. So that can be one set of select line inputs. And then z is just equal to 0, meaning that for that input, using that set of select line values, z is just equal to 0. Now for the next set, a and b being 0 and 1, z is 0 and 1, which matches the values that c takes. So z is equal to c. For the next set, a and b being 1 and 0, again as select lines, c is 0 and 1, and z is 1 and 0. That means that z is going to be equal to c complement. Then finally, for a and b both being 1, the final state of select line inputs, c is 0 and 1, but that doesn't matter because z is always 1, so z here is 1. Now when we implement this with a multiplexer, because we have two inputs, a and b, being used as select lines, we draw those here, and so we have two select lines. That means that we have two squared inputs, 4 inputs. The output is z, and you can either choose to write next to the inputs the state that allows that input to be selected or not. Generally, they just flow from top to bottom in order of least significant set of inputs to most significant set of inputs. So when a and b were 0 and 0, that means that the top input is selected, which was what we determined here, that's 0. For the second, when a and b are 0 and 1, that corresponds to this condition, z is c, and so forth, c prime and 1. Okay, so let's do a more complicated example with 4 inputs, a, b, c, and d. So again, we're going to use a, b, and c as select lines and block off different values. First, 0, 0, 0. Now d is 0 and 1, and z is 0 and 1, meaning for that set of inputs, z is equal to d. When a, b, c is 0, 0, 1, d is 0 and 1, z is 1, so z is just equal to 1. For the next set of inputs, Z is equal to D prime. So you can see there's a pattern here. You pretty much either get 0, 1, D, or D prime for every single input to the multiplexer. Z is 1 here. Z is 1. Z is D prime. Z is D prime, and finally for the last one, Z is also D prime. So this one would be implemented with an 8x1 multiplexer with select lines A, B, and C, and inputs D, 1, D prime, 1, 1, and D prime for all of the last ones. Let's just connect those, and output Z. So that's the general formula that you can use to implement a truth table for any function using a multiplexer. So multiplexers are very useful for this reason. They can implement lots and lots and lots of different functions.